So only when Yejil does this recording, then I remember that I should also record it. Thanks, Yejil.
You're welcome, Sesh.
Pardon?
I said you're welcome.
Ah, okay. Yep. Okay, so shall I wait for a, is there anybody expected? I mean, there's one more person who put a thumbs up for my, this one, but Acha, Bharati has come. Then, Dhanvarshani Murthy, she said she will come, but I don't know. Okay. All right, so let us start. So what I had promised you was that I will give you an alternative derivation and another criterion for convection to set in. Okay. And so let us do that. Okay. So in this, let us say that we need to remember the following points. Okay. Convection, condition, alternative approach. And so this is Landau and Lifshitz. And so for this, let us start by saying that we have the points to remember. First, we need to realize that any two thermodynamic variables completely specify my thermodynamic system. In other words, if, for example, I have taken an ideal gas and I specify an ideal gas of a given mass and I specify the volume and temperature, okay, rather the specific volume per unit mass and temperature. Every other thing like pressure, everything is completely determined. You are aware of this, right?
Yes.
Any two thermodynamic variables completely determines the thermodynamic system. So that's the first thing to remember. Second is, I will define a quantity S, which I call specific entropy.
Sesh,
Huh?
if only two variables are required, why when we are defining microstates every time, like when it's an open or closed system, we have three variables like energy, volume, temperature. Every time we'll include three variables, right?
Where while doing microstate? No. This is I'm telling from a completely thermodynamic point of view, not statmic.
Okay.
So in the sense that it may be to do with the fact that things are averaged out. Wait a minute. So, okay, can you just repeat it in the microstate, what you are saying?
Every time we'll include three variables to specify the total number of microstates. Like energy, volume, and temperature, I guess, for the...
No. Energy and temperature will be related, no?
Okay.
Okay. And also, actually, when you're talking about thermodynamic systems, you are probably not talking about a microstate.
Yeah.
Okay. So now you have S, which is a specific entropy. And then I have Cp, which is the specific heat capacity. And then I call something volume, but this volume is not total volume, but specific volume. And when I say specific, I mean per unit mass. All right?
Yes.
Okay. And so the other thing which you should remember is volume per unit mass is just inverse of density, because density is mass per unit volume. Okay. And then we have various thermodynamic relations, which we will list here. One is del V by del T, where V is the specific volume. Sorry, del V by del S. Del specific volume by del specific entropy at a given pressure will be equal to the temperature divided by specific heat capacity del V by del T at some pressure, at temperature. Now, these are things I'm just giving you. These are all part of that, I think, Maxwell's relations or something. Then we have del S by del T. That is the temperature variation of specific entropy at a given pressure is equal to Cp by T. And then we have, I think it is correct. Okay, let me see. Okay. And then we have del S by del P. When change in specific entropy per unit change in pressure at constant temperature is equal to minus of change in specific volume per unit change in temperature at a given pressure. And then we define a parameter beta, which is equal to 1 by specific volume del specific volume by del temperature at a given pressure. For ideal gas, what is it? What is beta for ideal gas? Hey.
Sometimes proportional to,
Sorry, what is it?
say, proportional to P.
No.
1 by P, sorry.
1 by B?
P pressure.
No. I mean, you just recall what is ideal gas, then you should be able to trivially get it.
Temperature proportional to?
Beta is proportional to what?
Temperature.
Are you sure? You're close.
Inverse of temperature.
Inverse of temperature. Okay, and then you can get this in the following way. For ideal gas, beta is equal to 1 by T. And how do we get this? We get this by saying for ideal gas, the specific volume is proportional to temperature. It means volume is equal to some constant times temperature. I take log of both sides. I mean, okay, this is, okay, sorry. For ideal gas, at constant pressure, right? Is that one of those Charles' law, right?
Yeah, yeah.
Okay, V is proportional to T, so V is equal to kappa times T. And then I have, I take log V is equal to log kappa, which is a constant, plus log t. Differentiate. So I have d del ln p by del t is equal to, this is 0 and this is 1 by t. Okay, right?
Yeah.
Okay, and so this is del v by del t 1 by v, which is equal to 1 by t, and this is what is defined as beta. Okay. All right.
Yes.
Okay. So we are now armed with all these things, and we also have the picture. Okay, let me just copy that. Okay, we have this picture here. Okay, for the convection thing. Okay, so we can just put it in a separate box. I mean, don't think that there is a ceiling which is a box and the blob is touching it. Okay. Okay, so now we just reiterate what are the assumptions we are working in. We said we assume that at the initial level, the inside and outside things are same. That is, rho I is equal to rho O, Pi is equal to Po, and Ti is equal to To. And now the specific entropy inside and outside is also equal. Entropy per unit mass inside and outside. Is that okay?
Yes.
Okay, fine. So now we then know that Pi prime is equal to Po prime. And that is because of, we had assumed a pressure equilibrium. That is, as the system goes up, it goes sufficiently slowly that it, at every point of time, it is able to reach a pressure equilibrium with the surrounding. So pressure inside and outside will be same at all points, in particular at the end point. Okay, so Pi prime is equal to Po prime. And then I had said that this is adiabatic. So the specific entropy inside initially will be same as specific entropy inside at the final point. The entropy does not change because there is no heat exchange.
Yes.
Okay, fine. Now I will just define the following things. I will say now what is rho I. Now I will call rho as a general variable for density, and I will take this to be a function of, I can do any two thermodynamic parameters, basically pressure and entropy, specific entropy. So I choose these two thermodynamic parameters, pressure and specific entropy, and I can define my density. And so what does it mean? It means the density inside the blob is equal to the density function at pressure inside at the initial point, comma SI. Are you with me?
Yeah.
Similarly, rho I prime at the final point will be rho at Pi prime, comma Si prime. rho O is equal to the density rho, because the gas inside the blob and outside the blob is the same nature of the gas. It is not hydrogen inside and oxygen outside. Okay, and that is why this function rho on P and S remains same for whether it is inside or outside. You get the point?
Yes.
See, the dependence of density on the thermodynamic parameters depends on the nature of the gas. Since it is the same gas which is within the same type of gas, although at a different thermodynamic state, since it's the same type of gas inside and outside the blob, this function on thermodynamic parameters remains same. So it is same function, but at a different value of pressure and density, which is PO comma SO. And rho O prime is equal to rho of PO prime comma SO prime. Are you with me?
Yes.
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 Bharti?
Sir, yes, sir.
Bharti?
Yes, sir.
Is it okay?
Okay, sir.
Okay, fine. So this we have. So now what is the convection condition? We already saw, okay, our assumption, we have started with rho I is equal to rho O. That is initially both are same, which means rho as of, so these are same. Okay, fine. And so if for convection, the blob should be pushed up by buoyancy at the upper point. Okay, that is what is convection, right? When the new point is to be pushed up. Okay, which means that I need rho I to be rather rho O to be greater, rho O prime to be greater than rho I prime. Is it okay? The density outside at the final point is more than the density inside the blob at the final point, so that by buoyancy, the blob will go up.
Yeah.
Okay. Then what does this mean? This basically means that the function rho evaluated at PO prime comma SO prime is greater than rho at PI prime comma SI prime. See, actually, if you look at Landau, he has written it in such a terse manner that he has not explained any of these things. He has just used it as a function and finished the whole thing in half a page. So just, so this will, when you're going through that, this will help you. Okay, so this is what we have, convection condition. But we know that we know that the entropy inside the blob is the same. So Si prime equal to Si. Right?
Yes.
This is the condition. Okay. Si prime equal to Si. And also I have PO prime equal to Pi prime, because there is pressure equilibrium always. Okay. So from these two, I get rho PO prime comma SO prime should be greater than rho PO comma SI. All right.
Yes, sir.
I have
Yes.
replaced Pi prime on the right side by PO prime. Oh, sorry. This one. Okay.
Yes.
Yes.
And then SI prime by SI. Fine. But I know that SI is equal to SO because initial conditions are the same at the initial point. So these two imply that rho times PO prime comma SO prime should be greater than rho PO prime comma SO. Is that okay?
Yes.
So now you see the beauty of what has happened. I have reduced the convection condition without any reference to what is inside the blob. Completely the atmospheric parameters determine the convection condition. You realize that?
Yes.
Yeah, because I just want to know what is outside at different points. That will tell me the convection condition. Okay.
Yeah.
And now what I do, I do some Taylor expansion. I have rho of PO prime SO prime is equal to rho of PO comma SO plus del rho by del PO dPO plus del rho by del SO dSO, where dPO is equal to PO prime minus PO and dSO is equal to SO prime minus SO. Okay? All right? It's the first term in the Taylor expansion. And
Yes.
similarly, I write rho PO prime SO is equal to rho PO comma SO plus del rho by del PO. Here I have to keep SO constant. Here I have to keep the PO constant. And here I have to keep the SO constant, dPO, and that is all because SO and SO are the same.
Yeah.
Okay. And so what does this mean? So when you compare these two, what happens is these two cancel out. So it means that rho PO prime comma SO prime greater than rho PO prime comma SO implies from these two that del rho by del SO PO DSO should be greater than 0. Okay?
Yes.
Yes.
Okay. And since delta Z is positive, it means del rho by del SO at PO DSO by DZ is greater than 0. So see, I have got it into some partial derivative of rho and entropy change for the convection condition.
Sis,
Okay.
what did you just do? Just divide.
I just divided both sides by DZ.
Okay.
Okay. Fine. And now del rho by, okay. Now I use the fact that rho is equal to 1 by specific volume. These two imply that minus 1 by V square del V by del SO PO DSO by DZ greater than 0. Since V is greater than 0, this implies that del V by del SO PO DSO by DZ is less than 0. Because there's a minus sign. Okay?
Yeah.
Okay. Now I invoke these relations which I had about del V by del S. Okay. Yeah. Now I had the relation which I had shown earlier is that, I mean, I had actually that Maxwell's relations, del V by del S at constant pressure is equal to temperature by specific heat at constant pressure times del V by del T at constant pressure. This is one of the thermodynamic relation. And from these two, I immediately get that T by Cp del V by del TO PO into del SO by del Z should be less than 0. With me?
Yeah.
Okay. And since T is greater than 0, Cp is greater than 0, I have del V by del TO PO DSO by DZ less than 0. The convection condition. Okay. I mean, just reminding, this is not the end of the derivation. This is for having convection condition. I'm repeating this because Landau, for some reason, works. The inequality will be opposite because he is trying to get the opposite condition when convection is not possible. Okay.
Okay.
So just be careful when you are referring to that book.
Okay.
Okay. So del V by del T naught PO is less than 0. Now, V is proportional. So, okay. So, with increasing temperature, volume increases, which means that del V by del T naught P naught is greater than 0, which means condition for convention is ds naught by dz is less than 0. Okay.
Yes, yes.
Okay, so this means, so this has been reduced to a very simple thing. In the atmosphere, with increasing height, if I find that the entropy per unit mass is decreasing, then I will have convection.
Okay.
Okay, now this is not the end of the story. But here you have to be careful. Is it always true? Remember, we are only talking about fluids. We have not yet gone to an ideal gas. I have not yet used this thing about beta proportional to 1 by T. It's true for any fluid. Now, can you comment on this condition? Do you have a situation where some fluid increases in volume when it decreases the temperature?
For some polytropic index, it might happen.
No. Okay. Yeah, but I'm talking about a very common thing.
Water.
Exactly.
Below
Anomalous
4.
expansion. Below 4 degrees centigrade. Okay. Hey, are you with me?
Yeah.
Yes.
Okay. So it means that for this, the convection condition will switch. That we will come to later. But let us now focus on the usual thing where volume increases with temperature. Okay. And so now, so this quantity SO is equal to S as a function of PO, comma, V. You see, here I should, I've been a bit careless. While writing rho, I have written rho O. But V, I have just done V. It's actually VO. It is the volume per unit mass of the outside atmosphere, not inside the blob. Okay, so technically I should have. Okay, and wherever. Okay, so this is what it is. Are you okay with this? Hey.
Yes, yes.
Sir.
Okay, fine. So this is this one. So I can now write dSO by dz, which is what I have to calculate on the right hand side here, is equal to del S by del P at PO dPO by dz plus del S by del V. Oh, sorry. Del S by del V at constant pressure del. Is it correct? No, just 1 minute. I goofed up. Okay, just 1 minute. Just do that. T by dz. Just okay, I have done some mistake while doing this. I'll just correct it. ds naught by del t, dst by del t. Sorry, no. I will not use this, but I will use the temperature outside as a variable. All right. Are you with me? I mean, sorry, it is not volume, but I'm using the two thermodynamic parameters of pressure and temperature use. Okay.
Okay, sir. But
So this and this implies, okay, so this implies that this quantity should be less than 0, which means that del S by del P at TO dPO by dz should be less than del minus of del S by del P PO dTO by dz. Okay. Now, I am talking about a situation where the system is almost in hydrostatic equilibrium. All right.
okay.
Okay. Which means that in the unperturbed form, dP naught by dz should be equal to minus the acceleration due to gravity and rho O. Okay. I mean, basically, you take the dz on the other side, it is a decrease of pressure into rho gh delta z.
Okay.
Okay. And so, from these two, I have del S by del P T naught minus G into rho naught is less than minus del S by del T at PO dt naught by dz. Okay, which implies that del S by del P TO G rho U is greater than del S by del T PO del T naught by dz. Because I have removed the minus sign, so the inequality flips. Fine?
Yes.
Okay. Now, let us see what is del S by del T. We had del S by del T at constant pressure is equal to Cp by T, which we had already shown earlier, which we had already mentioned earlier, right? This one. Okay. And so this is there. Okay. And I need del S by del P. I also have del S by del P at T naught is equal to minus del V by del TO at PO. Both these relations we had, the thermodynamic relations, right?
Yeah.
This one, okay? And now I use both these over here, and I get minus del V by del TO PO into G rho O is greater than, now the minus sign here because of this minus sign, is greater than Cp by T dTO by dz. Okay? And this is equal to minus 1 by V del by del T naught PO into G. Because V equal to 1 by VO equal to 1 by rho O. Okay, we can put it as this one. Greater than Cp by T, T naught by dt naught by dz. Okay? Now, what is this object? This is equal to minus beta. Right? I told beta into G is greater than Cp by TO dTO by dz, which implies that dTO by dz should be less than minus beta G minus beta G TO by Cp. You see this beautiful relationship now? Completely on the basis of the temperature gradient, I can now decide whether convection takes place or not. Hence, for convection, I need the simple relations dt naught by dz should be less than minus beta G T naught by Cp. So if I know the beta, I know G, I know the temperature, and I know the specific heated constant pressure, I can decide what temperature gradient will lead to convection and what will not. Are you with me?
Yes.
Now there is one more interesting thing. For ideal gas, I have beta equal to 1 by T, which implies that dTO by dZ should be less than minus G by Cp. It's a simple relationship for convection. All right.
Yes.
Yes.
Okay. And now look at it. It says something very interesting. It says that suppose, you will generally think that when will convection happen? When the temperature below is higher and temperature above is less. Correct?
Yes.
Okay. But it says something more. It says not to, so that in other words, the temperature gradient is negative. With increasing height, the temperature decreases, so there is convection. Right? Warm air goes up and so on.
Yeah.
Okay. But this says something more. It says that that is not sufficient. It has not only to be negative, it has to be sufficiently negative. If suppose it doesn't decrease as fast as G by Cp, although the temperature below is higher, convection does not take place. And that is why if you keep water in a pan and keep it on the gas, immediately in the immediate vicinity of the bottom of the vessel, temperature is higher. So temperature gradient is less. But you will find that convection currents don't set up immediately. It takes some time for the gradient to be sufficiently negative so that convection can take place. Do you get it?
Yes.
Yes.
And so, let me use this. Just 1 minute. Where was it? We drawn something. Just a minute. I had drawn something for. Oh, this is for today. This is different. A minute. Is this the one? No, this was not the one. This. We had drawn something now. Is it here? No. I'm scale. Just a minute, huh? I actually drawn some picture for explaining this. And I'm just trying to locate where that has gone. I mean, if you're those who initially joined, I was drawing those vertical lines and rotating them and so on, right? It was for that. Where it has gone. I don't know, I'm sorry. So what I was, this is bad. These two. This is the one. No, not this is the one. This is the one. Okay. Oh. Okay. No, this was the one I was doing. Okay, sorry. Okay, so fine. So this is what I wanted to show. And I will remove this for clarity so the other lines don't appear. Okay, so what it says is these lines, parallel green lines, all have a slope of minus G by Cp. Okay. Now what it says is, suppose I have a profile of the atmosphere where it goes something like this. Okay. Now this slope is greater than minus G by Cp, because remember it is a negative slope. So this is greater.
Yeah.
Okay. So although the temperature decreases with height, no convection takes place. All right.
Yeah.
On the other hand, suppose I start heating from below. So suppose, so now, okay. Okay. So suppose initially I start with a flat profile. Okay. And I start heating it, and it first becomes like this. Okay, so here the heating is there at Z equal to 0. So the temperature increased. However, temperature is not increased sufficiently to push convection. If I keep heating it more, it will go like this, and then the convection will start.
Yeah.
Okay. The other feature is what I was telling that day, that if suppose you have a situation where the surface temperature has increased, like if you have sun starts shining, surface temperature increased. And okay, so initially there is a gradient of this kind, suppose even some kind of a gradient like this. And now the surface temperature started to increase because the sun is shining. And this becomes something like this. Okay. Now what happens? At this point, if left of this point, there is convection, so there is movement of air here. On the right of this, convection condition is not such a way, but so because of lack of buoyancy, it will settle down here. So this is a region where from below and above, the air will start settling down, condensing. And when there is moist air, it will bring fog along with it. And this is the origin of fog. And this is called the temperature inversion region. Okay. So temperature inversion region is a place where the as you go up, convection condition transits to no convection condition. Is it clear?
Sasish, can you repeat once?
Okay, so what I'm saying is, suppose initially you have the temperature gradient like this, okay,
Yeah.
in the atmosphere. And after the sun starts shining, just the surface gets heated first, right?
Okay.
So the immediate neighborhood gets heated. So this becomes, in the immediate neighborhood, it becomes like this.
Yeah.
Okay. Now, in this region, dt naught by dtz is less than minus g by cp. Remember that is minus, it is steeper because the point is a negative slope.
Okay.
Whereas here, it is dt naught by dz is greater than minus g by cp.
Okay, sir.
So it means that the matter will flow in this direction, and here the convection flow direction, and it get collected over here at this height.
Okay.
And that is where the fog cloud starts coming up. That is why Delhi fog every day in winter in newspaper you say that flights have got delayed and so on.
Yeah. Okay.
This is the reason.
But why does matter from the higher altitude come to that temperature in some region?
Oh, that is because I said because the reverse condition is the blob is heavier, so it will settle down. So if a
Oh, yeah.
perturbation is there, it will come back to the original position.
Okay, so it's the weight.
Pardon?
It's the weight then.
Because of weight, yeah. Because it's heavier than the surroundings.
Okay.
Okay. All right.
Yes.
Okay. So this is the whole physics of convection, and this derivation I found in Landau only, this direction, because I feel this is, although the way you derive is a bit complicated and involved in thermodynamics, but the final result is fantastic. Okay. Yeah. Okay, let's have a break for 5 minutes and then we will continue. I am very sorry it got delayed because my driver's child has some emergency medical condition, so we're trying to fix up things with the doctor and so on. So that was the thing. Okay. Right. Just a minute. Are others there?
Yes.
Yes.
Yeah.
Yeah. Hey, sorry for this, huh? Yeah. Is the screen sharing on? No. Yes, okay. Okay, so there is just one thing which I want to mention, that about this anomalous expansion, what happens? See, when you have, okay, for the case of okay. for the case of anomalous expansion. What do I have? I have got del V by del T at constant pressure is less than 0. Okay. This implies that beta is less than 0. And let me not use beta equal to 1 by T because that's the case of ideal gas. I'm doing it for a general one. And so I have this equation here. So I have the convection condition is dt naught by dz is less than, as before, minus g beta to by cp. But now that beta is negative, this is equal to g beta by to by cp mod. So the criterion is now these lines which are there, okay. Yeah, I will just, I want to copy these lines again. And remove this also. Now, these lines are no more sloping downwards, but these are like this because beta is negative now. Okay. Okay. Now, what this means is so it means that even when there is a uniform temperature, no. Okay, so the convection condition, so if suppose, so this quantity, if it is even 0, it is flat. Even then, when this temperature is below 4 degrees for water, there will be a convection. And in fact, even when the temperature gradient is like this, that is, the upper reaches have a higher temperature than lower temperature, then the lower temperature guys will come up because of anomalous expansion. Okay, so this is where, so this is for when beta is less than 0. You get it?
Yes, yes.
Yeah, because previously you always had this negative slope. Now the point is, even when the temperature increases with height, you will have convection. Okay, provided the region where we are talking about temperature is less than 4 degrees. Okay.
Yeah.
And the other interesting thing is, suppose you have okay, so suppose you have, yeah, okay, fine. So this is what it is. This is what you should do with convection. Okay, so I was just thinking whether to go to radiative transfer or talk about a bit of stellar evolution for a change. Okay, so let me just do something a bit more light. Okay, which will be, because today it was heavy. Yeah. Okay, okay. What is this? Fine. So now let us now look at some general things in astrophysics. One is, it's a bit disconnected from what we are doing now. I'll come back to radiative transfer later. So just to change gear a bit. Okay. Measurement luminosity of stars. Now, when you have stars, conventionally, the unit used is something called magnitude. Okay. And there are two characteristics of this. Magnitude depends on log of luminosity. Okay. And the other thing is, more magnitude implies less luminous. Okay, so it's a very strange kind of a unit they use, and there's a reason for it. I will tell you, let us come to the second one first. You see, if a star is bright, it is easy to see, right? You agree,
Yeah.
right?
Yeah.
Okay. It means if a star is less bright, it is more difficult to see. So the magnitude is actually some kind of a measure of the effort required to see the star. And that's why it goes reverse. Okay. And then there is this thing about log. Why log? You see, most of the human perception is always a log scale. For example, when you want to measure loudness, you measure a decibel scale. Now, decibel is the log of sound intensity. Similarly, when you have earthquake, you have a Richter scale, which is log of the intensity of the thing. Now, the question is, of course, why is it there's a log? It is because if a star is twice, or if a star is half as bright, it turns out that the human eye does not need double the effort to measure to see it. Okay. It actually doesn't go linearly, but it goes as a log. That is, if suppose, okay. Okay, so I will come to it when we come to the formulae. Okay. So now, first of all, you have this concept of luminosity. Okay. Now, luminosity is equal to energy emitted per unit time. Okay. And then you have energy flux, which is intensity, is equal to energy received per unit time per unit area. Now, if suppose there is a source which is isotropic source, which is emitting energy at equal rate in all directions, then this energy, if I draw a sphere of radius r or radius d, then this energy is spread over an area of 4 pi d square. And so, energy received per unit time is equal to energy emitted per unit, energy per unit area is energy emitted per unit time divided by 4 pi d square. And that is where the intensity of an object of the light goes as 1 by r square. Are you with me?
Yes.
Hello? Okay. So this is the intensity. Okay. So for a given source, the intensity will be by square. Okay. And so if the same source is a different, so I call it ID. If the same source was at a different distance, capital D, it would have been I capital D, which means ID by ID is equal to D square by D square. Okay. Just a minute. D square by D square. Fine. Now, as I said, due to historical reasons, the measurement of intensity is done in terms of magnitude, and ID by I capital D is defined as 10 to the power minus 0.4 MD minus MD. That is, if the same, if suppose you have a star which is at a place small d, and there is another, and the same star is kept at capital D, then the magnitude differences is related like this. And so I have MD minus MD is equal to minus 5 by 2. It's the conventionally, it is the 10th base which is taken. Okay, is the definition clear?
Yes.
Sesh, D is the radius, right?
Okay. D is the radius. No. So what I'm saying is there is a source. There is an observer. There is an observer at a distance D. And there is another observer at a distance. Oh.
Sesh, I think your screen is lagging. I don't know if it's only for me.
What? No, it's
Yeah,
okay. I can see that.
There's a bit of
Oh,
latency here.
huh. Is that okay now?
Yeah.
Okay. And this, oh, sorry. And this is capital D. So I'm considering the two things. Okay.
Okay.
Okay. Then there is something called the absolute luminosity. Now, absolute luminosity is the defined as the apparent luminosity. So, okay. So this intensity is also called apparent luminosity. All right. So what happens is there is something called, because actually the problem is the astronomer's way of doing things is very different from physicists, because I always prefer to work with intensity. But the astronomers generally do another thing. They say that I will normalize all the intensities as if the thing was at 10 parsecs from me. Okay. So let us do the following. So suppose I define, so suppose I have I is equal to, ID is equal to L by 4 pi d square. Okay. And now I say that D is equal to 10 parsecs. And suppose I keep, okay, so in this case, suppose what I was doing, suppose capital D was 10 parsecs. I take that as a standard. Then the magnitude of this star, wait a minute. The magnitude of the star, when the star is kept at 10 parsecs, magnitude of star, if the star is kept at a distance of 10 parsecs, is called absolute luminosity. I mean, see the absolute magnitude, sorry. Okay. Now, you see, because the reason is this. You see, physics-wise, L and I are two different things. But in order to measure, give a measure of L, so what I do is L is equal to I 10 parsecs into 4 pi 10 parsec squared. Okay. And this I call, the magnitude corresponding this intensity, I call the absolute magnitude. Do you get this?
Yes, yes.
Okay. It's a very strange way of doing things, but historically, this is what it was done. So let me do that. Okay. Parallax. So this is d square. So like, for example, take this one. Here, I have MD minus M capital D is equal to minus 5 by 2 log 10 ID by I capital D. Okay, so this is equal to minus 5 log ID by ID to the power half. But we are looking at the same star. So L is the same, 4 pi is the same. And so this is basically equal to minus 5 log of D by D. Is that all right?
Yes.
D by D. Okay. Now, if D is equal to 10 parsecs, I call MD as the absolute magnitude capital M. That's the definition. Okay. And so I have MD minus M is equal to 5 should be plus because I flipped these
Yeah,
things.
yeah.
Okay. Yeah. So it will be MD minus M is equal to log of 10 by D, where D is measured in parsecs. So this is how you define.
Didn't we say I capital D is proportional to 1 by I capital D squared?
No, no, it's okay. Let us do it again. Okay, that will be better. So I have, where was it? Oh, okay. So I have okay, so I have ID by I capital D is equal to 10 to the power minus 0.4 MD minus MD. Okay, and so I have, and this is equal to L by 4 pi D square which means that D square by D square is equal to 10 to the power minus 0.4 MD minus MD. Is that okay?
Yeah.
Okay. And now let us do it systematically slowly. This is equal to D by capital D is equal to 10 to the power 0.2 MD minus MD,
Yeah.
which is equal to 10 to the power MD minus MD by 5. And so MD minus M capital D is equal to 5 times log base 10 D capital D. And so I write MD minus capital M, which is the absolute magnitude, is equal to 5 log 10 D by 10 parsecs.
Yeah.
Okay. Yeah. So that is the thing. Okay. So it means for the same star, further it is more the magnitude because more the effort to see it.
Yes.
Okay. Yeah. I think we'll stop today. I'm too tired.
Stays, I have one doubt.
Huh.
So they define this quantity called 1 Jansky, right, in intensity. Like that electrical engineer who first got a signal.
Yes, yes, yes.
Like, how did he get that value? Like 10 power minus 26 or something.
Oh, they must have just normalized it to some known sources. That's all.
Okay, like just like for decibels, we divided by 10 power 5.
Yeah. That's right. That's right.
Okay.
Okay. Okay. So I will see you next Saturday. Next Saturday, I'm not sure, but we will do something. Okay. Yeah.
All right.
Bye.
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 Bye.